Hi, my name is Fabio and this is my NEA test plan. So we're going to go ahead and start testing objective 1, 1.1 and 1.2. So objective 1 is concerned with entering in data to specify the host. 1.2 is more about catching errors. So first we're going to do a normal test, we're going to do 4 and we're going to get no exception. As you can see, it proceeds to the next stage of the program, so you can say that is a pass. Okay. Stop and rerun the program, and now we're going to enter in 294, and that is not going to be a valid user ID, and therefore we're going to have an exception thrown. As you can see, exception is thrown and we need to restart the program. Now we're going to enter in some non-integer characters to see about how the validation of this program works. It's not a valid ID, legal argument exceptions thrown, and we have to go and restart. Okay, so we can tick all 3 of those off. So that's test number 1, 2 and 3. Test number 4, 1.1, we're going to enter in Fabio after the next step of the program. So we're going to leave it 1 and Fabio. And then that proceeds to the next step program, which is what we expect with into concern where it goes after that. Take that as a tick. Next, we're going to enter in Marvin. Now Marvin is not on the database, and as such, oh wait, at least I put that. So we're going to enter in 1 as student ID and Marvin. Marvin is not on there, so it's going to be a no match, and we're going to have to enter a new name. And once we're here, we can take that off, and here's the test by entering Marvin 10 times, and it should output the console each time asking for a new name. So just go Marvin, copy and paste that. And as you can see, it will go on indefinitely to ask for Marvin or a new name until a correct name is entered. Right, and next we have test number 7. We're going to enter in Ben when asked for a host. And it's going to ask us to enter a surname because there are multiple students in the database with the name Ben, and then we're going to enter in 10. But if we look at test number 8, when we get into 10, it's going to ask, we've been asked the surname, it's going to determine which person. But after entering surname, the exception is from in the program because Ben 10 does not have a policy coming up. So this is the second layer of a questioning that not every person you might enter might have a party. So we're going to enter in 10, and as it happens, that student has no upcoming parties, invalid host. So tick those off. So now we move on to test number 9. This is a test of objective 2. Objective 2 is to store the data taken from the user's social media accounts. So what we are testing here is that in our database, how we correctly take in the information so that it can be used in the program. The data should include the user's full name, username, followers list, and the following list. So this is information about the user's accounts, the student themselves, and who they follow, so that we can be able to map them and recreate a graph later on. So we're going to open up our SQLite, and first thing we notice is this is a table of all the students. Got student IDs, first names, surnames. So this covers all the areas required for any information we need to hold about students. Then we go to accounts. Each account has an account ID, as you can see from in incremental order with usernames, and then it maps to student. As you can see, one student can have 2 accounts, and this plays in later when we're creating the graph, because how can we map one student as following two things and things like that, and one account following the same person on two different accounts, and what does that mean. So we played around with that. Then we go to the follows table. It's a huge table as there's a lot of following going on. It's a big network, and there is a composite key which maps one account to another, and this means that this account follows this account. So account 11 right now, which is now following account 1 and account 5. So this will create +1 on the proximity score between account 1 and 5 when we're creating the graph later. So that's objective 2, which is to hold all this information in the table. So we can take that off. Okay. Test number 10, objective 3. It's a normal type of test, and now we're getting into the graph and the processing of our data. So we're going to enter 1 and ash, and once we've already entered valid host, the program will run to its end and it will have an output. But we're not concerned with the output right now, because the first bit we're going to test is objective number 3. Objective number 3 is about mapping the invitees to the host. So in this we have stated that we want each individual to represent it as a node, and a node is essentially a point that has connections and can be referred to in other places. It's just a point, a hub in like a web. That's it. So we need a way to be able to represent individuals as a node, and sharing followers with someone should be represented as connection from them. So that sharing of followers we were talking about earlier should be represented here somehow. We should be able to see some form of information that relates to that, and this should essentially create a map from user to host using these two principles. And so the way we have opted for this is to go around the route of using a graph. Now a graph can be represented in an adjacency matrix or an adjacency list. In this program we use an adjacency list because for a matrix it can be quite inefficient if it's a sparse graph. So when we run the program we put in 1 and ash, and in the first section there will be a graph, and that should be the graph that we talked about in the expected result. The graph is outputted as an adjacency list, as mentioned. Listening people are connected through mutual followers, bidirectional connections, so a connection will appear in both people's connection list. So what we're looking for is an adjacency list. We don't care about exactly what the information inside it is, what the data is inside it, if it's correct, if it can be processed, if it can be used. But objective 3 is about creating that graph and making sure that the adjacency structure is met, and that there is now a viable path, or if there is no path, that can be represented in this graph. I'm going to enter 1 and ash, and this is the first section we're talking about. See, this is the rest of the program. We're going to ignore that for now, and in this first section of the output we see that we have an adjacency list where there's bidirectional connections. So if we were to say Sai, he's connected to Benji and Gavin. Benji also has Sai in his list with the same connection value here. This shows that it's bidirectional, so either way that you go along this route from Benji to Sai or Sai to Benji, you will be moving 6 across, and that is what we wanted in our expected result, so we can take that as a pass. Test number 11, test objective 4.1. So objective 4 is to have a system in place to evaluate two people's closest. So as you can see in this, there's these integers all over. These are supposed to represent how close these people are. So how close Sai is to Benji, how close Fabio is to Gavin or David. And there's multiple parts of objective 4, so we're going to read those right now. 4.1 is to apply an algorithm to produce an integer value that represents how close the relationship between two people are to each other. So 4.1, it seems that we're done here because we see integers values that represent the connection, but it's a little more complicated than that. 4.1.1 is to work out the proximity rating for people based off data across all of a person's social media accounts, and the algorithm should derive answers from the collected data of both individuals. So this value has to come from somewhere. It's not being sent randomly. There's an algorithm behind it that is working out the score, and we'll be able to see that later on when I'll show you some graphs that where the data which should match the data that we have right here, and if it does, then we have passed this test. 4.2 is to use the derived value as a weighted connection between two individuals, and that again will be demonstrated with the graph that has been made visually, as the data is quite large, so it's hard to represent. And 4.3, the value produced in the algorithm should be compatible with the algorithm objective 5. So this part of the objective 4 hints at the fact that in our assigning of these values, a higher weight means a closer, tighter knit connection with a person. However, in an optimization algorithm such as a shortest path finding algorithm, a lower weight is the positive, it's the better, because it's supposed to be the shortest distance. So to be able to use such an algorithm, you need to invert this weight, where the highest weight should now be 1 and the lowest weight should be as far away from the highest weight as it was before. So the highest weight here is 6 and the lowest weight is 1, so they should be 5 apart. And when we're going to use the optimization algorithm, we can represent this data in a way that the optimization algorithm can process. But first, we're going to go to test number 11, 4.1, normal. You enter in ID and valid host. Program starts formulating to represent the invitation list and show where the weight is associated with each connection. There are weights assigned to each connection to represent the social distance between two people. So that's the first part. That there is a integer value, and we can say we passed that test. Test number 12, 4.1, normal. The graph is output alongside each connection list in the adjacency list, and the integer value representing the weight of connection accompanies it. A second graph is an output all underneath it, and the connection with most weight in the original graph has been removed as a maximum, and all the weights are recalculated as the maximum original weight, so that the people who are closest have less distance between them. This one talking about the recalibration of the weights so that it's being used by the optimization algorithm. So here we can see Benji 6. 6 is the highest weight in this graph. It comes up a few times. 6 here, 6 there, 6 there, 6 here, and 6 there. So 6 is the highest weight, and whenever we see 6 in our new graph, we see 1s. 1, 1, 1, 1, 1, 1. And in this way we can see that has been recalibrated correctly. So Gavin was 4, he's now 3. So it's 2 away from 6, it's 2 away from 1. 3 is 3 away from 6, 4 is 3 away from 1. So in this way we can see that the graph has been inverted. We can take that off. 13, 4.2, normal. Enter ID. So the adjacency list output should reflect the connection of graph 1. So graph 1 is printed down below. So this graph should be represented here, and as you can see, user is Fabio. So here we go. Fabio, Gavin 3, David 1. Yes, Gavin 3 to David 3, Fabio 3, Benji 2, Manav to 1, Site is 3. As you can see, this graph is being mapped here in every connection. So we pass that test because the data in the database was made to reflect this graph, so that program producing this means it's meeting objective 4.2. Test number 14, objective 5 and 6. The testing of the shortest path algorithm based off the output. So earlier in the documentation we did a dry run of the Dijkstra shortest path algorithm, and we came up with this answer, that the path would be Ash, Benji, and Fabio. Average distance should be 2, and as you can see, based on the data on graph 1, so the data we used in our dry run was this. We then put this data in our database, the program produced it, then ran our optimization algorithm, and as you can see there are predictable results. The shortest path between Ash and Fabio is 8, the path is between Ash and Benji, the path is Ash, Benji, Gavin, Fabio, the average is 2.0. This was done in our dry run, it has been reproduced by our program, therefore we can be sure that the algorithm works. So I haven't read objective 5. Objective 5, determine best path from user to party host. So this is to use an algorithm to determine the path with the highest average proximity score. Program should determine the path that should be taken average, and the algorithm should be a shortest path algorithm. So we have used Dijkstra, so 5.3 check. 5.2, the program should determine the path should be taken and the average proximity score. We determined the path and the average distance, and we have used an algorithm. We use Dijkstra, so tick off any part of objective 5. And objective output to user. Output path of names of the people we should ask, output average proximity score, and output information about the party. So we output the path, we output the average distance, and we've output the information about the party. The party is on the 24th June 19th at 8 o'clock on 10 Downing Street, London. So that's to say that test number 14 is a pass. Test number 15, 5 and 6 normal. Testing short based off output. This is based off results of graph 2. On graph 2, the user is no longer connected to this main section of the graph. There's no way they could be invited, and as that should be reflected in the output. So we're going to enter in 23 and Ash. It creates a graph, and then it tells us there is no route to host, invitation is impossible. This is what should have been output based on the results of graph 2. If there's no path to this main section, there will be no path to the host, and therefore no invitation is possible. And objective 2.3 is about this section here, and also about outputting the information. It still does that, so we still meet objective 6.3. And 6.3 is met when you put in 1 and Ash. As we said, 2024, June 19th at 8:10 Downing Street. And that concludes